All right, so get this. We're diving into a mathematical puzzle today. It's going to twist your brain a bit.
Oh, yeah.
Yeah, we're talking about, like, exponents, but on another level. Imagine, like, exponents, but then doing exponents to those exponents.
Whoa.
Forever.
Sounds a little crazy.
Right. So it's called tetration, and honestly, it gets pretty wild pretty quickly.
So for this deep dive, we're actually trying to solve a specific problem, right?
Exactly. And it comes from a Tim Scientia video.
Ah, I've seen that one.
Yeah, they ask, like, what value of x would make, okay, get this, x to the power of x to the power of x and so on forever equal to 2.
Okay, so it's not just theory. We're getting our hands dirty with an actual equation.
Yep. And the video starts off with this really elegant solution, but then, bam, throws a curveball that I totally didn't see coming.
Yeah, so they highlight how the inner part of that infinite power tower.
Oh, infinite power tower. I like that.
Yeah, it's a pretty cool visual, right? So that inner part, it's basically the same as the whole thing, right? Because it goes on forever. So they say, okay, let's just replace that whole inner tower with a 2, because that's what the whole thing supposedly equals, and we get the equation x squared equals 2.
Hold up. How did we get from this infinite tower to just x squared? I'm a little lost there.
Right, okay. So imagine, like, it just keeps going, right? The tower. So any piece of it, no matter how far down you go, it's going to be identical to the whole thing. It's like those Russian nesting dolls, you know? Each one has a smaller version of itself inside.
Oh, okay, I get it.
So in our infinite tower, the inner tower is just another infinite tower, so it also has to equal 2, just like the whole thing.
Got it. It's like those mirrors that reflect each other infinitely, right? So we just keep seeing the same thing over and over.
Precisely.
So then we get that x squared equals 2, which means the square root of 2 is our solution for x. Elegant. Case closed, right?
Well, not quite. That's where the video throws that curveball I mentioned. They do the same thing with a different equation. This time, x to the power of x forever equals 4. And guess what? Same solution pops out. X equals the square root of 2.
Wait, hold on. That doesn't make any sense. How can the infinite power tower of the square root of 2 equal both 2 and 4? That's just not right.
That's the paradox. And to get to the bottom of it, the video turns to computer simulations.
Computer simulations?
Yeah.
How do you even explain infinite tetration to a computer? You can't just type in an infinite number of exponents.
Yeah, no, you can't. That's where these things called recursive functions come in.
Okay, I've heard of those. But remind me.
So imagine you're climbing a ladder, right?
Okay, I'm climbing.
You start at the bottom, the first rung, and that could be, say, x to the power of 1. That's our base case.
Gotcha.
Then you need a rule that tells you how to get to the next rung based on where you are now.
Okay, so like step up one rung at a time.
Yeah, exactly. So in our case, each new rung is x raised to the power of the previous rung.
So each step builds on the one before it.
Precisely. And the computer just keeps following that recipe, climbing that infinite power tower one step at a time.
That's pretty slick.
It lets us explore patterns that would be impossible to do by hand.
So what happened when they ran this simulation? Did it give us an answer for the square root of 2?
Well, the simulation showed that the infinite power tower of the square root of 2 does converge to 2, just like that initial solution suggested.
So mystery solved.
Not so fast. It actually made things even more confusing, because why didn't it also converge to 4?
Ugh. Okay, so we're back to square one. It's like we have a suspect, but their alibi checks out. We need a new angle, right? Where do we go from here?
Instead of just looking at individual equations, let's take a step back and define a function, we'll call it fx, to represent the infinite tetration of x.
Okay, so instead of getting lost in the weeds of this one specific tower, we're trying to see the bigger picture.
Right. We want to figure out for which values of x this whole infinite tetration thing actually makes sense. Like, does it actually converge to a real number?
Makes sense.
And that's where these things called fixed points come in.
Fixed points.
Yeah. So if our function fx equals, say, y, then we know that x to the power of y must also equal y. That means y is a fixed point.
Okay, I think I'm following. But, like, why is that important?
Well, it's a key idea in figuring out how functions behave when you keep feeding them back into themselves. It's like, if you put y into the function x to the y and you get y back out, then y is like in a game of tag. It stays put. It's fixed.
So these fixed points are like the anchor points for our function.
Exactly. And understanding them is key to unlocking this whole tetration mystery.
Okay, I'm intrigued. But how do we find these fixed points? Do we just have to guess?
Not quite. There's a visual way to think about it. Imagine plotting the curve z equals x to the y. Then, on the same graph, we plot the line z equals y. The points where they intersect, those are our fixed points.
Ah, okay, so it's like a treasure map, where X marks the spot. Only in this case, X is where our function stays put.
Exactly. Now, as we change the value of x in our equation, the exponential curve shifts around. Sometimes the curve and that line, they might not intersect at all, no fixed points there. Other times they might just touch, like at a single tangent point. And sometimes they might cross over each other, giving us two intersection points.
Okay, so different values of X give us different scenarios. But how does this all tie back to our infinite power tower?
Well, if there's no intersection, the tetration just keeps growing forever. It diverges to infinity. No good. But if there's one intersection, one fixed point that suggests there might be a nice, stable solution where the tetration converges.
Okay, that makes sense.
Mm.
But what about when we have two intersections?
No, that's where things get really interesting. That suggests there could be multiple solutions, which might explain that weirdness we saw with the square root of 2.
Right. Okay, so we have these different scenarios, but we still don't know which ones will actually give us a convergent answer. How do we figure that out?
Well, we need to focus on that special case, the tangent scenario.
The tangent scenario.
Yeah, where the curve and the line just barely touch each other. This is a critical point, where the behavior of the tetration can completely change.
Why is the tangent case so important? What makes it special?
Well, think of it like a tightrope walker. One wrong step, and it all goes wrong. The tangent point is that delicate balance point.
Gotcha.
And to understand what's happening at that point, we need to bring in some calculus.
Oh, calculus. Now we're getting serious.
Just a little bit. What we're interested in is the slope of that tangent line right at the point where it touches the curve.
Yeah.
And that slope, it's determined by the derivative.
The derivative. Okay, so like how steep the curve is at that exact spot.
Precisely. And get this, when we actually calculate the derivative and find that x value where this tangent scenario happens, we get this fascinating result. It involves Euler's number.
Euler's number. What's that got to do with all this?
Right, that famous constant, it's like it pops up everywhere in math. And here it is again, playing a crucial role in determining whether our infinite tetration converges or not.
Wow, math is full of surprises.
Totally. So you want to know what happens on either side of this special x value, this Euler's number thing?
Yeah, tell me, what's the big reveal?
Okay, so for values of x greater than Euler's number to the 1e, the tetration will always diverge to infinity. It's like trying to build a tower that's just too tall, it'll inevitably collapse.
Okay, makes sense.
But for values of x between 1 and that special Euler's number value, it converges.
So it's like this threshold, this Euler's number to the 1a. On one side, it works. On the other, chaos.
You got it. And to understand why this is, we can think about it like a staircase.
A staircase. Okay, I'm listening.
Imagine each step represents an iteration in our calculation. When x is less than Euler's number to the 1e, no matter which step you start on, you'll always end up moving toward the fixed point.
So it's like a slide that always brings you to the bottom, no matter where you start.
Exactly. But when x equals that special value, it gets tricky. You might converge, or you might not, depending on where you start.
So it's more like a seesaw. One side goes up, the other goes down.
Yeah, something like that. And if x is greater than that special Euler's number value, well, no matter where you start on the staircase, you're always going to move away from that fixed point.
Ah, okay. So it's like, I don't know, a broken escalator that only goes up.
Exactly. And here's the mind-blowing part. That derivative we talked about, it actually tells us which of these scenarios is happening. If the absolute value of the derivative is less than 1, it's like a gentle pull toward the fixed point, stability and convergence. But if it's greater than 1, it's a push away, leading to instability and divergence.
Wow, the derivative is like this hidden force shaping the fate of our infinite power tower.
Right. And this deep connection between calculus and tetration, it shows you just how interconnected math really is. Calculus, which can seem so abstract, it actually gives us this powerful tool to understand the behavior of complex systems like this.
This is blowing my mind a little. Okay, so we've figured out a lot about when tetration converges. But what about the other cases? What happens when it doesn't converge? I feel like there's more to this story.
You're absolutely right. We still need to talk about what happens when x is between 0 and 1, because in some of those cases, the tetration can oscillate between two values instead of converging to a single fixed point.
Hold up. So it's not just that it goes to infinity, but it like bounces back and forth?
Yeah, even though a fixed point exists.
Whoa, that's crazy. It's like there's this home base for our power tower,
Yeah.
but it can't quite decide whether to settle down or not.
Exactly. It's a really interesting phenomenon that reveals just how complex tetration can be.
Okay, my brain is officially fried. We've covered so much, but I feel like we've only scratched the surface. There's still that paradox from the video
Yeah.
with the square root of 2 and 4, and now we've got this whole oscillation thing.
Don't worry, we'll unpack all of that in the next segment. Stay tuned.
All right, so we left off talking about these oscillating cases. Like, our infinite power tower just can't make up its mind.
Right, it's got this fixed point, but it just keeps bouncing back and forth.
Like a ping pong ball, right? Bouncing between two values.
Exactly, and it highlights this kind of tension between stability and convergence. Just because there's a fixed point doesn't guarantee that the tetration will actually land there.
So it's like, I don't know, a moth drawn to a flame, but it never quite lands.
Yeah, that's a good way to picture it. It's drawn to that fixed point, but something keeps pushing it away, creating this endless loop.
Okay, so what determines whether our tetration settles down or gets stuck in this loop? There's got to be some kind of rule, right?
Great. There is. And remember how we talked about the derivative at the fixed point, how it tells us about stability? Well, it plays a big role here too.
Okay, so remind me, how does the derivative fit into all of this?
Think of the derivative as a kind of force acting on the tetration.
Okay.
When the derivative at the fixed point has an absolute value less than 1, it's like a gentle pull towards the fixed point, making things nice and stable so the tetration can converge.
Smaller derivative, stronger pull, more stability.
That's it. But when the absolute value of that derivative is greater than 1, it's like a push away from the fixed point, creating instability, preventing convergence.
Gotcha. So that explains why it diverges sometimes. But what about this oscillation thing? That's just weird.
That's where things get really interesting. Often in these oscillating cases, the derivative at the fixed point is negative.
Negative.
And its absolute value is still greater than 1.
So it's both repelling and creating this flipping back and forth.
Exactly. That negative sign in the derivative creates this alternating pattern, pushing the tetration away from the fixed point in one direction and then back in the other, leading to this endless oscillation.
Wow, so it's like the derivative is this conductor leading the orchestra of our tetration, telling it when to converge, diverge, or just get stuck in this crazy dance.
I like that analogy. And, this kind of behavior isn't just limited to tetration. It shows up in all kinds of iterative function.
Iterative function.
Yeah, any function where you keep applying it to its own output, they can show these same kinds of patterns.
So this isn't just a quirk of infinite power towers. It's a bigger thing.
It's a fundamental concept in dynamical systems,
Yeah.
systems that change over time.
Oh, okay.
And it pops up all over the place, from physics to economics to biology.
Okay, well, we've got this oscillation thing sorted out, but now I really want to get back to that paradox from the video. Remember where we thought the infinite tetration of the square root of 2 could be both 2a and d4? Did we ever figure that one out?
Right. That was a good one. It really shows why it's so important to understand what's going on behind the scenes before just blindly applying a method.
So what went wrong? Was our logic flawed?
The issue is that we can't just substitute the entire infinite tower with a single value, like we did, without thinking about the consequences. It ignores the whole idea of stability and those fixed points.
So just because the infinite tower appears inside itself, we can't treat it like a single number without things getting messed up.
Exactly. It's like assuming that just because a car has wheels, it can drive on any surface.
Yeah.
The engine, the tires, everything matters. Same with tetration.
Okay, that makes sense. But I'm still confused about how our method gave us 2 different answers for the square root of 2.
Well, remember, our critical value, Euler's number to the 1m. The square root of 2 is actually less than that value, while 4 is greater.
Oh, so it all comes back to that Euler's number threshold.
Yep. Because the square root of 2 is less than that value, its infinite tetration does indeed converge to 2. Our method just happened to stumble onto the right answer, even though it wasn't really valid. But because 4 is greater than that special value, its infinite tetration doesn't converge to 4. It actually diverges to infinity.
So it was just coincidence. Our method was wrong, but it gave us the right answer by accident. Sneaky.
It happens sometimes. It's a good reminder that a simple solution might be hiding a lot more complexity. We always need to be questioning our assumptions.
Right. Math isn't just about plugging numbers into equations. It's about understanding the concepts, thinking critically.
Absolutely. And even a seemingly simple system like tetration can have a lot of depth and complexity waiting to be explored.
Okay, well, I feel like we've finally climbed to the top of this infinite power tower.
Mm-hmm.
We've learned a lot about tetration, But what about when those power towers aren't made up of whole numbers? What about fractional powers?
Fractional power towers. Now that is where things get really wild.
It's like trying to imagine a staircase with steps that are half a step high.
Exactly. It's like, what does exponentiation even mean in that context?
My brain hurts just thinking about it.
But that's the beauty of math. It
Yeah.
lets us push those boundaries and explore concepts that we never could have imagined before.
All right, I'm ready for the next challenge. Let's dive into this world of fractional and irrational power towers. Fractional power towers. I'm still not sure I get it. Like, how can you have half a tower?
It does seem strange, right? It's like, what's half an exponent anyway?
Exactly.
But believe it or not, we can actually make sense of it. We use a tool from calculus called analytic continuation.
Analytic continuation. Okay, you've lost me.
Okay, so imagine you've got a puzzle, but some pieces are missing, right? Analytic continuation is like finding those missing pieces and fitting them in perfectly.
Okay, I can kind of see that.
We have our TETRATION function, which works for whole number heights, right? And with analytic continuation, we can extend that function smoothly to include those fractional heights, the missing puzzle pieces.
So we're taking something that works in one situation and kind of like stretching it to work in others.
That's a good way to think about it. And what's really cool is that this idea connects to complex analysis, too.
Complex
Like
analysis.
you know, with imaginary numbers and stuff.
Okay, now we're really getting into the deep end.
Right. It opens up a whole new world of mathematical possibilities. We can start asking questions about whether these non-integer power towers behave the same way as the integer ones.
Right, like do those rules about convergence and fixed points still apply?
Exactly. It's like we've discovered a new island and we're trying to figure out if the laws of physics are the same there.
I like that. So there's still a lot more to explore with this whole tetration thing.
Oh, absolutely. We've just scratched the surface. We started with this simple question about infinite power towers, and it's taken us on this incredible journey through calculus, fixed points, and now even complex numbers. It's amazing.
It really is. I think it's a great reminder that math is about so much more than just memorizing formulas.
Right. It's about exploration, making connections, discovering patterns.
And for anyone listening out there, what's the key takeaway from all of this? What should they remember?
I think the biggest thing is don't be afraid to ask questions. Don't be afraid to explore. Even if something seems impossible or confusing at first, there might be a whole world of fascinating ideas hidden beneath the surface.
Exactly. And even if problems seem simple, there might be a lot more going on than meets the eye. Keep digging deeper, keep asking those questions, and you'll be amazed at what you discover.
Couldn't have said it better myself.
Thanks for taking this deep dive with me. And for everyone listening, thanks for joining us. We'll see you next time.